Welcome everyone. Today we'll start chapter 11, Common Collector and Common Base Amplifier. This is the outline for today's lecture. Common Collector Amplifier. When the load resistance is small compared to the collector resistance, the voltage gain of common emitter stage becomes small and the amplifier may become overloaded. The equation for voltage gain for same amplifier is RC parallel RL upon RE dash. So let us understand first of all what is this problem or what they want to convey here. Because the equation is this RC parallel RL upon RE dash, we know that if the value of RL is reduced, if load resistance value is less, then our numerator part will become lower, hence your gain will be reduced. So this is the reference slide from previous chapter. Here in common emitter amplifier we were considering, in this example we were considering RL 10 kilo ohm, hence RC, small rc is equal to RC parallel RL. We were getting this value as 2.65 kilo ohm and hence our voltage gain was RC upon RE dash 2.65 upon 22.7 ohm is equal to 117. So we were able to achieve a voltage gain of 117. But assume if the value of load resistance, that is a load that we are going to drive, if it is very low, for example it is 50 ohm, in that case this parallel combination may be lower than 50 ohm and this value might be less than 50 ohm, and what happens to our voltage gain? It will be here the value around 50 to 40 ohm divided by 22.7, our voltage gain will be approximately 1 to 2. So from 117 our voltage gain will be reduced to 1 to 2, only 1 to 2. So that is a problem when the load resistance is higher in case of common emitter amplifier. So when your load resistance is the load resistance is lower. So when RL is lower, we cannot use C amplifier. So one way to prevent the overloading is to use a common collector amplifier, or it is called emitter follower. This type of amplifier has a large input impedance and can drive small load resistance. We will see in brief. Common collector amplifier circuit diagram will be like this. The input signal is coupled to the base. The input signal is coupled to the base and the output signal is taken from the emitter. The output signal is taken from the emitter. Figure 9.0 shows an emitter follower amplifier. Because the collector is at AC ground, collector is connected to VCC, so definitely it is AC ground. The circuit is a common collector amplifier. The input voltage is coupled to the base, which sets up an emitter current and produces an AC voltage across the emitter resistor. This AC voltage is then coupled to the load. So whatever AC voltage is available here, that is coupled to the load RL. The voltage diagrams. The total voltage between the base and ground is this. You can see it is a VB voltage. This is VBQ, that is a DC value, and this is the AC value. It has a DC component and AC component, as you can see. The AC voltage writes on the quiescent base voltage, that is VB, that is a DC value. Similarly, figure C shows the total voltage between emitter and ground. Here also we will have DC emitter and the AC emitter current. AC emitter voltage. This time the AC voltage is centered on a quiescent emitter voltage VE. So this AC voltage is centered on the DC emitter voltage VE. The AC emitter voltage is coupled to the load resistor. This output voltage is shown in figure D. So the load voltage or the V out is shown in D, which is a pure AC because we are using the coupling capacitor. The reason the circuit is called an emitter follower is because output voltage follows the input voltage. So here we want to say that input and output are in phase. On the other hand, on common emitter amplifier, input voltage and output voltage are out of phase, 180 degree out of phase. Since there is no collector resistor, a total voltage between the collector and ground equals the supply voltage. If you look at the collector voltage with an oscilloscope, you will see only the constant DC voltage, that is VC. So collector voltage is a constant DC value. There is no AC signal on the collector because it is an AC ground. Negative feedback. Like a swamp amplifier, the emitter follower uses the negative feedback. Here we have shown the swamp amplifier and the common collector amplifier. In swamp amplifier, you know that we are adding additional RE which will provide the negative feedback. With the emitter follower, the negative feedback is massive because the feedback resistor equals all the emitter resistance. In swamp amplifier, we are adding a small resistor here, which is not the complete emitter resistor, but a small resistor which is giving you the feedback. But here, the complete RE will act as a feedback resistor, so your negative feedback will be massive, will be large. As a result, the voltage gain is ultra stable. The voltage gain will be stable, distortion is almost null, and the input impedance of the base will be very high. Because of this characteristics, the emitter follower is often used as a preamplifier. We will see later on where we are going to use the amplifier. The trade-off is the voltage gain because your voltage gain will be reduced and it will be maximum 1. Okay, that we will see with the equation what is the value of voltage gain we are getting in CC amplifier. The next is AC emitter resistance. The AC emitter resistance small re is called the combination of Re parallel RL. This is the external AC emitter resistance which is different from the internal emitter resistance Re dash. So if you just recall the circuit for CC amplifier, then this Re and this RL, the parallel combination of this Re and RL is called the AC emitter resistance. Small re is equal to Re parallel RL. So here the equivalent circuit, AC equivalent circuit using T model is shown. You can see here that the value of Re shown here, Re dash is shown here. So what will be the value of V in? V in will be whatever current I is flowing plus this resistance plus this resistance. So I is equal to Re plus Re dash. What will be the value of V out? V out is taken from the ammeter. So that is IE into Re. So your gain will be Re upon Re plus Re dash because IE IC will get IE and IE will get cancelled. So that becomes your final equation for the voltage gain. Usually designer makes Re much greater than Re dash, so the voltage gain equals to 1. This Re is very much greater than Re dash, so you can ignore this Re dash. So Re upon Re will be 1. This is the value we will use for the analysis. In this slide, we can see the AC equivalent circuits, T model in figure A, pi model in figure B. We will utilize this pi model in the next slide. Why is an emitter follower called an amplifier if its voltage gain is 1? Because it has a current gain of beta. The stages near the end of system needs to produce more current because the final load is usually low impedance. The emitter follower can produce large output currents needed by the low impedance loads. In short, although it is not a voltage amplifier, the emitter follower is a current or power amplifier because you know the equation of power is I square R. So if your value is R is lower, that is output impedance is lower, then only helpful parameter will be I square. So your current, if your current is high, then your power will be I square R will be high. Input impedance of the base. So refer this pi model of CC amplifier. Looking at this, what will be the value of V input? V input is this. So you can say that whatever current flows through this, multiply this resistance, that is IE into RE plus RE dash, that will be your V input. So your V input is beta IB because your IE is represented as beta IB, RE plus RE dash. And your V out is taken from here. So your V out will be IE into RE. So from this equation, if we bring IB down, then V in by IB is equal to beta RE plus RE dash. So input voltage upon input current will give you the input impedance, that is input impedance for the base, that is Z in base, will be beta RE plus RE dash. For troubleshooting, you can assume that RE is much greater than RE dash, which means the input impedance is approximately beta RE because this RE dash is very lower compared to RE. So we can ignore RE dash and Z in base will be almost equal to beta RE. The step up in impedance is the major advantage of an emitter follower. Small load resistance that would overload a CE amplifier can be used with an emitter follower because it steps up the impedance and prevents overloading. The input impedance of the stage. So if you want to measure the input impedance of the stage, then here the parallel combination of R1 and R2 will come in parallel with Z in base, so that is called Z in stage. This we already know Z in how to calculate Z in stage, Z in base in the previous chapters. R1 parallel R2 parallel beta RE plus RE dash, that will become your Z in stage. So now based on this, let's solve one example. What is the input impedance of the base in figure given below, where beta is equal to 200? Also you need to calculate the input impedance of the stage. So first of all, let us calculate VB, that is a DC value. VB will be 10 upon 10 plus 10 into 10. So you will get 5 volt. VB is equal to VB minus VE. Using this equation, you can easily get the value of VE, that is equal to 4.3 volt. And if you have VE 4.3 volt and your RE is also 4.3 kilo ohm, so your IE will be 4.3 divided by 4.3 K is equal to 1 milliampere. Now, because each resistor in the voltage divider is 10K, okay, this we have calculated 1 milliampere here. Okay, IE is equal to 1 milliampere. Therefore, the AC resistance of the emitter diode, that is RE dash, will be 25 millivolt upon IE, that is equal to 25 ohm. Now, the external AC emitter resistance that is Re parallel RL is equal to Re 3 kilo ohm. Since the transistor has an AC current gain of 200, the input impedance will be beta Re plus Re dash 605 kilo ohm. Now, the input impedance, that is Z in stage, is parallel combination of R1, R2 and Z in stage. So, sorry, Z in base. So, R1 parallel R2 parallel Z in base. So, we know that this is 10, this is 10 and this is 605. So, parallel combination of this will be lower than the lowest value. So, it will be 4.96 kilo ohm. So you can see this in a different way also, that 10k parallel 10k will be 5k and 5k parallel with 605k. So approximate value will be 5k. Because 605k is much larger than 5k, troubleshooters usually approximate the input impedance of the stage, that is Z in stage, as the parallel of biasing resistor only, 10k 10k, 5k, and here you are getting 4.9k, almost both are same. Second example, assuming the beta value 200, you need to find out the AC input voltage to the emitter follower of the figure. So we need to find out the AC input voltage at the transistor, available at the base of the transistor. So this is the AC equivalent circuit given, that is a Z in stage here 5k. So we know that if we assume the input voltage is 1 volt peak to peak and Rg is 600 ohm, then this will become definitely a voltage divider. So V input is equal to 5k upon 5k plus 600 ohm, that will be 0.893 volt. The next example, what is the voltage gain of the emitter follower given in this figure? Beta consider 150. Also, what is the AC load voltage? So we want to find out the AC load voltage 2. The DC base voltage is the half of the supply voltage, that is 7.5. You can consider 4.7, 4.7 parallel combination. So that will be half of the 15. So it will be 7.5. IE you can calculate RE dash, same method. Now RE is RE parallel RL, that is 1.66 kilo ohm. Now the voltage gain is 1.66 upon 1.66 plus 8.09, that is 0.995. So we are using the voltage gain equation here to RE upon RE plus RE dash. Okay, RE 1.66 upon RE plus RE dash. RE upon RE plus RE dash to find out the voltage gain. We are getting almost 1. The input impedance of the base will be how much it is? Beta Re plus Re dash. So that is 250 kilo ohm. The value of Z in base, that is 250 kilo ohm. This is much larger than the biasing resistors. Therefore, to a close approximation, the input impedance of the emitter follower, that is Z in stage, will be 4.7k parallel 4.7k, that is 2.35k. We know that even if we put the exact values, that is 250 kilo ohm parallel 2.35, then almost we are going to get the value is near to 2.35 kilo ohm. So the AC input voltage will be the voltage divider of this Z in stage plus the source resistance, that is 600 ohm Rg. So it will be 0.797 volt. Using this, the AC output voltage will be V out is the voltage gain into the input voltage, that is 0.793 and this is 0.797. So almost your V input and V out same because our voltage gain is approximately 1.